For this year's competition, the York University Rover team has decided to completely revamp our approach to building the rover. Instead of designing the typical wheel-based rover most teams favor, we opted into a tread-based design. The treads allow for a lower surface pressure, making it more effective when traversing rough terrain. Our design also features a lower center of gravity, enabling the use of a larger arm. This stronger arm can be used to clear obstacles as well as restabilize the rover should it ever fall over. When the arm is unmounted, the rover will be able to execute inverted operations.
The science team has been researching extensively for the past few months to investigate the best methods for determining the presence of life in regolith. This rover is a modular build, so we can alter attachments depending on the task at hand. This keeps the rover's weight down as well as protects the scientific instruments during other tasks. The first step in any science plan is being able to locate a suitable sample to assess. For this task, we will be looking for a combination of indicators for the potential of life. Some of these include mud cracks, which could indicate a previous presence of water, and desert varnish, which could indicate manganese-excreting microbes. We could further narrow down potential sites by locating the lowest altitudes, as water is most likely to be found there. The sample retrieval module includes a long auger and a retrieval tube, which will pull up soil samples from 10 centimeters down using a screw pump mechanism. This sample is then deposited in a sterile container where it is stored. It is then brought back to the lab for further analysis. Such testing includes mass spectrometry analysis and pH testing. Once the auger is finished, 2 probes, humidity and sensor, will be inserted into the sample hole to gather more data at a sample depth. Furthermore, onboard sensors like the Geiger counter and atmospheric sensor will record data on the sample site. Finally, the sample will be observed under a microscope. We will be looking at the soil type as well as any possible microbial life. All of these methods in conjunction should be enough to prove, or at least strongly indicate whether or not life is or has been present at the site.
Our electronics team has been hard at work converting our homegrown software packages to ROS, the robotics operating system. ROS, as described by its developers, is a collection of tools, libraries, and conventions that aim to simplify the task of creating complex and robust robotic behavior. The chief benefits of ROS are the wide variety of open libraries available for the platform and the built-in WebSocket-based networking which streamlines the communication between independent systems. This built-in networking makes it simple to divide deployment efforts across many small teams, drastically increasing our development throughout. Our software systems are divided into a collection of independent nodes governing actuation, sensors, and control. Most of our custom software is written in Python due to its compatibility with ROS and availability of the libraries, and the team's overall familiarity with the language. The base station for our rover consists of a 2.4 GHz router, an associated moving parabolic antenna, a desktop computer, a monitor, and 2 joysticks. During the competition, the parabolic antenna will continually update its bearings to point to the rover's locations, ensuring reliable communication over large distances. The rover is governed by a centralized Odroid computer maintaining a core networking node and several independent subsystem nodes. An onboard router handles communication with the base station. Actuation is controlled by 3 independent Arduino Nano microcontrollers controlling the arm, drive, and scientific instruments respectively. Sensors are handled in a similar way to actuators, with the independent microcontrollers handling regular input from an ultrasonic array and publishing it to the rover network. Cameras located on the arm effector and central chassis also publish a compressed video stream to the base station and autonomous subsystems. One of 2 RTK GPS chips will provide approximate location data when out of contact with the base station. Sensors are handled in a similar way to actuators, with independent microcontrollers handling regular input from the ultrasonic array and publishing it to the rover network. Cameras located on the arm effector and central chassis also publish a compressed video stream to the base station and autonomous subsystems. One of 2 RTK GPS chips will provide approximate location data when out of contact with a base station and a centimeter level accuracy from differential GPS methods when the base station is in contact. Our rover will have a toggleable autonomous mode which fulfills 2 functions. For autonomous traversal tasks, it will take a set of GPS coordinates and attempt to navigate to them. For the path planning, we are using a multipath adaptive A-star. If the rover is out of contact with the base station during a teleoperation session, it will also attempt to return to the last known location with a strong signal. Basic hue circle techniques and color filtering allow it to hone in on spherical targets at short range.